Okay, hi Leah. I forgot to record, so here's where we are. And we want some video of you after your wisdom teeth. We want to see if you're loopy from the medicine. So make sure you give us some video of that. All right, so metals and nonmetals achieve this noble gas configuration two different ways. Nonmetals can achieve it either by gaining from metals to complete their outer shell, or by sharing with other nonmetals to complete their outer shell. I'm not going to write that again. You know this. This is not new. Okay? So in general, let's see. Move this up here so I can extend that. When two nonmetals react, this is the first dot. To form a covalent bond. They share electrons in a way, there are exceptions to this, but they share electrons in a way that completes the valence electron configurations of both atoms. Okay, whether they need to share one or they need to share two, they share as many as they need so that they get a full outer shell. Okay, but when a nonmetal, this is the second dot, and a representative metal, a representative metal is group 1 or 2. We can't really talk about the metals that have multiple oxidation states here again because the whole 8 is happiness thing doesn't work for them, right? God bless you.
Thank you.
So when we have a nonmetal and a representative metal react to make an ionic compound, a binary ionic compound, they react in such a way, I will just say, they react so that the nonmetal achieves the noble gas configuration. This is kind of a lot. I don't know how else to say it though. Of the group 18 element in its row. The metal, the group 18 element in the row before it. Precede 2 E's and then a D? Or C-E-D-E? Precedes. That's not right. That's not right. That doesn't. I think it's this. I don't know. Precede, not proceed. You think it's this?
Yeah.
Okay. All right. That's the question of the day. What I'm saying, either way, is that if you are oxygen and you're going to make an ionic compound. When you make an ionic compound and you react with a metal, you will gain 2 and take on the electron configuration of the noble gas that's in your row, which is neon. So when oxygen has a -2 charge, its configuration is the same as neon's, 1s2, 2s2, 2p6. And when magnesium, a metal, makes an ionic compound, it will lose 2 to look like the noble gas that's in the row before it. So not argon, argon's in its row. It will lose 2 to look like neon as well, 1s2, 2s2, 2p6, okay? Remember, if you lose electrons, your charge is positive, and if you gain electrons, your charge is negative, okay? So the nonmetals will make negative ions, and the metals will make positive ions. Vitally important. Okay, so we have a sample problem coming up here next. And in that sample problem, they ask you to write the electron configuration and determine the charge on each of the following atoms when it forms its most stable ion. Okay? So the first one is magnesium. Now, magnesium is going to look or have the same configuration as the noble gas that comes before it when it's its most stable ion. That's what all that writing was about. So it will be 1s2, 2s2, 2p6. Because magnesium is normally this, right? This is normally magnesium. When magnesium, the metal, loses 2 electrons, it will now have a full outer shell. Okay? So this is your configuration when magnesium makes its most stable ion. And the form of the most stable ion will be Mg plus 2. I'll do a metal or non-metal, and then you could do C and D by yourself. If we have phosphorus, phosphorus is atomic number 15. You'll have 1s2, 2s2, 2p6, 3s2, 3p3, right? 15, 10, 15. Yep. So phosphorus will gain, count the blocks to get to argon. 1, 2, 3. It will gain 3, and those 3 go in its outer shell. So it will have this configuration. And since it's gained 3, its most stable ion will be P with a -3 charge. So really, if you think back to it, all that memorizing that you did with what charges things can have when they're in compounds, you really don't need to memorize it. As long as you know they'll gain or lose whatever to look like the noble gas that comes before them or after them. Okay, you just have to know they do it differently. The nonmetals gain to look like the noble gas that comes after them. So just it's like playing a board game. Count the spaces till you get to the next noble gas, and the metals go backwards to get to the noble gas that precedes them. So please do bromine and rubidium now. Bromine is going to be Br minus 1, and what will its configuration be?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6.
Okay, good. Any problems with bromine? Leah, did you get it right? Yay! Okay, let's do rubidium. What did you get for rubidium, Jenna?
I got RB plus 1.
Right, plus 1, go.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6.
Okay, so what would we call these two, RB and BR? They're like backwards of each other. What would we call them if they have the same number of electrons, right? They have the same electron configuration. They're isoelectronic, right? These two are isoelectronic. And I think that's coming up in just a minute to define. They have the same electron configuration. Who would be bigger?
You mean radius-wise?
Yep, radius-wise. Who would be bigger? Br. The less protons you have, the bigger you'll be. The more protons you have, the smaller you'll be. And Rb has what, 37 protons, and Br has 30, what, 5? Can't tell. 35. So since this has more protons, it would be smaller. This has less protons, it would be bigger. It's opposite, okay? That question also came up on the test. It was with the AS and the GA. Remember that one? You had to make your ions of AS. I think it was AS, yeah. And your ion of GA, and you had to see which one was bigger. Whoever had less protons would be bigger, right? If you don't remember it, it's going to come back to you in a minute. I mean the test, that is. All right, so from this, I don't know, I think we've kind of already been doing this, but determine the formulas when each of the following sets of atoms combine when they form a binary compound. Go ahead, do it. If K and Br make a compound, what's their formula? Okay, good. K's most stable ion is +1. Br's, yeah, you can see it. I don't know what I was thinking when I picked this color. K's most stable ion is +1. Br's most stable ion is -1. So the formula is KBr. Go ahead and do the rest, please. God bless you. And F. Good. Oh, that's way better. Good thinking, Lincoln. SRF2 works. AL and SE, Justine.
AL2, SE3.
Good. And Joanna, BAO.
BAL.
BAO. All right, good. All right. So now we have to talk about ion size. But again, this is all review from Chapter 7. Whether or not an ion is bigger than its parent atom depends on how the ion is formed. So ion size really depends on ion formation. A cation, which of course is a positive ion that occurs in metals, right? They will be smaller than their parent atoms. For example, Ca plus 2 is smaller than Ca. Account for this difference. Okay? Why would cations be smaller?
They have less electrons and the same number of protons.
Okay.
There's more.
They lose a shell. They lose a whole shell. So yeah, it's not just that they have less electrons, it's that they lose a whole shell of electrons, because sometimes you have less electrons and you're bigger, right? So calcium's configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. There are 4 occupied shells, right? And 20 protons. When you become the calcium ion, you've lost 2 electrons. Which 2? Your valence electrons. So the calcium ion is only 1s2, 2s2, 2p6, 3s2, 3p6, right? So you have, this has 3 shells, and this guy has 4 shells. Again, less shells, smaller whatever, all right? For an anion, which is a negative ion, they are larger than their parent atom. Because of electron repulsions and less Coulombic attraction of the gained electron. I'm using that word, that phrase.